Welcome to benzene, most likely the first aromatic compound you'll meet. Aromatic describes the compound as cyclic, planar, and with a ring of resonance bonds, allowing it to be stable. So what do you first need to know about benzene? Well, for the A-level exams, you'll need to know a little history. Benzene is a structure of 6 carbons and 6 hydrogens, and there was much debate on how this was structured. In comes August Kekule and his Kekule structure. He suggested the logical idea that the carbons were arranged into a hexagon and alternated single and double bonds like so. We can see that each carbon is bonded to a hydrogen, single bonded to a carbon, and double bonded to another carbon. This satisfies the 4 extra electrons carbon needs to have a full outer shell. This is all well and good, however it's not actually true. There are 3 problems with this structure that you must be able to answer. Number 1. Benzene doesn't undergo reactions that the Kekule structure should. So you notice the double bonds, they love to undergo electrophilic addition reactions. Break the double bonds and add in some new atoms. But benzene doesn't do this at all. It instead does substitution reactions by swapping its hydrogen. So the first point, benzene does not undergo addition reactions in standard conditions. Just mention the standard conditions, because you can actually force an addition reaction to happen, but we won't worry about that here. The second problem arises from the shape of the Kekule structure. See, again, it's the double bonds. They're shorter than single bonds due to the greater electrostatic attraction between the nuclei. So if we were to just imagine the structure, it would look very wonky. Instead, it's been determined that all of the carbon-to-carbon bonds in benzenes are all the same length. There simply cannot be any double bonds within the structure. So, point 2. All the carbon-to-carbon bonds are the same length. Thirdly, benzene is far more stable than the Kekule structure suggests. We can see this through the hydrogenation enthalpy. So this is when you add hydrogen to a molecule and measure the energy given off. So comparing cyclohexene structures, you'd expect the hydrogenation enthalpy to go up as there are more double bonds to hydrogenate. So from my lovely graph, you can see the higher the bar, then the more energy given off. With a single double bond, it is at 120 joules per mole. So with 2 double bonds, we expect it to be double that value, which is near enough at 232. So with the Kekule structure, boasting 3 double bonds, it must be triple the energy. But benzene isn't even close, in fact it's lower than the 2 double bonds. Point 3. Benzene has a lower than expected hydrogenation enthalpy. And these 3 points are all evidence against the Kekule structure. So what is the real benzene structure if it doesn't have any double bonds? Well, to answer this, we're going to have to take a look at the bonds themselves and the orbitals involved. See, on the carbon, there are 4 electrons available for bonding, but only 3 are being used. 1 for hydrogen and 2 for the other 2 carbons. That leaves 1 electron sitting in a p orbital on its own. So let's draw on the partially filled p orbitals on each of the carbons. And what occurs is that the p orbitals all overlap with each other, above and below the plane, to form a pi system. It is said that the 6 electrons aren't held between the atoms, but are spread between the whole structure. So if we were to describe the structure, we can say benzene is a planar ring of 6 carbons and 6 hydrogens, with a bond angle of 120 degrees. It has a pi system of delocalized electrons above and below the plane. and we can simply draw it as a hexagon with a circle in the middle to represent the pi ring. And that is benzene. Thanks for watching, folks.